In the United States, about 40 to 45% of all energy used in the United States goes to buildings. It's a huge amount. And if you incorporate, what Bob was saying before, if you incorporate the embodied energy of making that building, we're now between 45 and 50% of all energy use in the United States. And my topic is about net zero buildings. In net zero buildings, we can bring that 50% down dramatically, improving our air quality, our reliability on energy substantially in the United States. Unfortunately, nobody's doing it. I happen to do one of the biggest ones in the United States, 2 in the United States. But to date, we only have 35 buildings across the United States that are certified net zero. So what I'm doing is I'm going to give you a little education about net zero building. This is the public safety building. I led the team to be a net zero building on this particular building. Learning objectives, I'm going to talk about trends. There's a lot of policies out there to get people to go to a net zero building. How to do a cost-effective net zero building. Some approaches to low energy architecture. We're going to talk about the application of on-site and off-site green power. We're going to also talk about, we'll probably run out of time, but a behavioral aspect. If you can design a net zero building, but if the occupant doesn't get it, you probably won't achieve it. So, and lastly, I'm going to show you a handful of tools to use to analyze and study how to do net zero building. So let's run through these things. So if we take this building and analyze the energy use or energy cost or the carbon footprint, the idea to get to net zero is that you go through a design process to bring it down as low as possible, and then you go through a process of using green power, on-site and off-site, to make it so that it's net zero energy or net zero carbon or net zero cost over a year's period of time. That's the whole idea. So there's some trends out here. So one of them is the 2030 challenge. And the 2030 challenge says basically in year 2030 that we have net zero buildings. And this adopters are really being adopted by the big architectural firms, big engineering firms, some state governments and local governments. So their challenge is that steadily we get better with our buildings over time. Right now it's 60% better than a standard building. So over time we'll go from 2015 we'll be at 70%, which is next year, to 2030 where it's now net zero. So the other one that's being widely used is the LEED rating system. Oh, let me go back. So if you dive into the protocol on using the 2030 challenge, they're really measuring it on site energy basis. So it doesn't matter if it's electricity or natural gas, as long as you reduce those by 70%, you meet your goal. On the LEED rating system, they do it by cost basis. So everything is how much cost have we reduced in energy use. So that's a widely used, accepted methodology, but it's all done on cost, energy cost. And then we have portfolio manager from EPA, which is basically measuring it on a carbon basis or source energy basis. And it does what's your carbon footprint, and it has the capability to calculate those emission rates. Another one is the climate registry. Climate registry is being used throughout the United States in all kinds of sectors. And it's basically a counting process. And so it gives you, and it's used internationally, used by the Greenhouse Protocol on how to calculate the carbon footprint. So this is a very good method to use. So first thing you have to do is you have to pick one of these. Yeah, you got to pick how you're going to measure net zero, right? So the first one, the 2030 challenge, basically is measuring the site energy. And the second one is cost. And the third one is the greenhouse gas protocol. Now, if you do those methodologies and you do the calculations, you can see that if you have a PV array, they're different sizes. It's not consistent. So the first one is 1,200 kilowatts array. And basically, it's just looking at energy and offsetting how much energy the PV array is going to offset. The lead rating system is cost. So when you have a lead, when you do it on a cost basis, when you buy energy from the grid, it's at a higher cost than when you sell it back to the grid. So for example, you might buy electricity at 9 cents a kilowatt hour, but you sell it back to like 5 cents a kilowatt hour. And so making up that difference requires you to have a much bigger array. And then the last one, the greenhouse gas protocol, is analyzing it at a different rate. So the electricity is at a different emission rate. Natural gas is a different emission rate, and and selling it back to the grid is a different emission rate. And we'll get into those details. So this is an example. We're going to walk through a carbon footprint calculation just to show you how it's done. So this is a public safety building, and it's just now getting finished with their PV array. We have a megawatt offsite. We have about 380 kilowatts on the building itself. And so if we look at, in terms of energy, here's our electricity, part of the pie chart. Here's our natural gas. This is what's being generated on-site, and this is what's being generated on-site, off-site. So have we, just looking at that bar chart, have we achieved net zero? Yeah, right? So these two parts are bigger than these two parts. Right? So I'm confident that we'll get there. But that's not how we're measuring it. We're measuring it using the greenhouse gas protocol. So let's go through those calculations. So the first thing you have to do is pick, thanks Clive. So the first thing is you have to pick out your emission rates. So I'm an engineer, I apologize, but I have to do these calculations to show you. So if we have our energy source, so we have electricity, natural gas, we've got on-site green power and off-site green power, and here's the projected energy projection or use. Okay, so here's the emission rates. So for electricity, you have to figure out where you are in the United States, what grid you are, and then you have to pick out the emission rate for that area. In the Pacific Northwest, that's what we're in that grid, has a lot of hydroelectric, it has some nuclear, so it's much lower than if you look at Utah by itself. Okay, Utah by itself, we're a coal state, and those numbers would be much, much higher. But since we're in a grid that has a hydro and electric, or hydro and nuclear, our emission rates are much lower. So keep that in mind. And then we got natural gas, which is a direct emission, that's just burning gas. And that's, you just pick it off the table. And then the on-site green power, you notice it's 0. Now that's an interesting concept. So if you own the RECs, the environmental properties of the on-site, then that rate is 0 because all the energy that's being used in the building has no emissions because it's all clean energy. Interesting. Okay. If you go out and you sell that or you give it back to the utility, like you take their incentive, then you're back to this rate. You have to use the 109. So that's one of the points to keep in mind. If you're trying to get to calculate your carbon footprint, consider not taking the Rocky Mountain Power incentive because you're giving away the environmental properties. You'll have to buy it back. So keep that in mind. That's a very good point. And then the offsite, you notice this number is much bigger, 187, than the 109. Now the reason why it's so much bigger is because it's competing with new energy. So it's competing against natural gas turbines. And that's a higher value than just the base load of 109. So keep that in mind. You get a lot back when you sell it back to the utility, when you use the greenhouse gas protocol. Everybody gets that idea? I'm sorry, I'm an engineer. Gotta go through these. But it's an important concept, right? One concept is this is 0. Natural gas is half the emission rate. That's a very interesting concept, right? And when you put it back into the grid, it has a much higher rate, right, than if you just use the on-site. Okay, got it? So then what you do is you do what your greenhouse gas inventory is, right? This is what we use on-site. And so you just do your math, do some conversions, and we get, so our carbon footprint for the building is 484,000 kilograms of CO2. The next step is to try to figure out what the avoided emission, and that's all coming off your offsite. So our avoided kilograms is 896,000. Have we met the net zero definition to this point? Have I lost you all?
What was the last calculation?
So it's just the greenhouse gas emissions is 840. That's our footprint, right? And we're selling back this amount in carbon emissions.
Yeah.
So, so we get a negative 412. So we're, according to the greenhouse protocol, we're way beyond a net zero building. We're net positive, big time. Okay? Understand that concept? All right. So trends. Another trend that is out there that'll never get implemented with this Congress is the carbon tax. Right? There's environmental properties, or not really properties, but deficit when you use energy, right? And so when you do analysis for cost effectiveness, you really should bring those qualities into your calculation. So when I do, when I look at solar PV array, just don't do a straight, analysis. Bring in the environmental impact in using those kind of energy. And what I used here is 2 cents a kilowatt hour. So your payback, your real cost, or your real cost impact is much, much lower when you take that into account. So the other thing that you need to consider is another aspect of the 2030 challenge. The 2030 challenge was developed back here in 2002, and here's the challenge that came into effect in 2006. But there's another one that came into effect in 2011, which is basically the product. Building, how much energy does it take to build the building? So that's a different aspect on the whole carbon footprint question, right? So it's not just operation, it's how much do you operate and how much did it take to build the building. Now, that number is around 30% over a 30-year lifetime. So it's a big number. It's a big number. So the 2030 challenge for product actually does the same thing as the previous. It sets goals that in 2030 you have reduced that carbon footprint in building buildings by 50%. So how do you do it? Well, you use software, life cycle assessment software. And so I did some, real rough numbers. And I took a typical office building and made it steel office building versus a concrete office building. Right off the bat, I can see that the concrete office building takes a lot more carbon emissions to build that building than a steel building. And if you went to a wood frame, it would be lower than the steel frame, the steel building. So that's another aspect. Somebody has to make that concrete. Somebody has to make that steel. So you keep that into the mind of the carbon footprint for your building. So the real question is, how do you do this cost effectiveness, right? How do you do it so it makes sense? So what I've seen in the past is that, us architects, we just build buildings, we do some energy efficiency, it's a marginal improvement on the building, maybe 25%, and we call it a day, right? But if you put solar on a building like that, it's going to cost you megabucks, right? So, for example, public safety building, if we just did standard design processes, we would need probably a block and a half of PV to make this a net zero building, right? Very expensive. So you got to keep in mind that that's a very inappropriate way to do it. So what you want to do is you want to take your building here, your energy use here, reduce it as low as possible so the cost effectiveness of the green power is actually equal to the cost of the advanced design. So all of a sudden, we're not talking simple paybacks. We're actually evaluating on how big is the array and how much does that cost. So it's a different calculation. So for the public safety building, here's the public safety building. It's now not a couple blocks of PV, but it's still a fairly large area of PV to make this building net zero. Everybody get that idea? Right? For the public safety building, we had to do everything possible to bring down those energy use. And still, we ended up with a lot. So, advanced design. If you work with an energy engineer, these guys that do energy models, one of the things you want to do right off the bat, get them to do this graph. Plot me on a monthly basis your baseline building versus what you're being designed. Okay, so baseline building, if you look at this, curves like this, right? This is all cooling energy up in this portion, right? Well, in Salt Lake, we can use evaporative cooling very effectively. It's virtually free in this state. We also have a lot of daylighting outside, right? if you design the building correctly, you can actually make it inverted. And so your peak demand is not in the middle of the summer, it's in the middle of the winter. So that's what you want to look for, right? Have you done this? Have you figured out that you got good daylighting, you got good mechanical system that actually use evaporative cooling? That's how you do it. So another approach to green architecture is make your building skinny, right? And this is a NREL research support facility in Golden. Thank you, Golden. And it's a fantastic building, fantastic in many ways. And it's a net zero building. It's the other building that I talked about that's of the same size as the public safety building. And their footprint is about 60 feet wide. So this is south facing. You can see that it's only 60 feet wide. The reason why it's 60 feet wide is so they can get daylighting from both sides of the building and light that footprint. So you walk into this building in the middle of the day, there's not a light on. It's perfect. It's perfect, right? In fact, I think 60 is a little too wide. I think it should be less than that. But the idea is what we want to do is make those footprints or width, or floor plan width, as small as possible so we can do daylighting throughout the entire space. So that's one of the strategies. The other interesting thing about the NREL is the sloping roof. So if you slope your roof, you can put your PV panels side by side. You don't have to space them or worry about shadows. So that's very important. So the other concept is when you do these analyses and figure out cost effectiveness, is that the mechanical system is the #1 most expensive part of the building in terms of energy efficiency. And so what you want to do is, you just don't want to buy the mechanical system for the baseline building. You want to buy the mechanical system for the design building. And getting mechanical engineers to do that correctly is always difficult. So we're going to run through a couple of these. So one of the things you want to do is study mass. Mass has an impact on performance of your building. You want to study daylighting, as we mentioned. In fact, daylighting studies for this particular building shows that I have no worse than 340 lux, which is about 334 foot candles, to about 460 lux, which is about 46 foot candles, all the way back to about 30 feet, and using light shelves. So on the public safety building, for example, we've got light shelves. We also have this pane here is tinted for comfort issues. The upper part is clear, and we have a light shelf on the inside. We also have blinds that are automatic, so when there's direct sunlight into the space, it closes. The blind's light, so you still get daylighting effect. So also consider going beyond a standard window, right? So what we use is a triple pane window. We actually have 3 layers of low E on those windows. I could have used low argon, but I didn't go there. But when you look at the whole big picture about going to net zero, triple pane window starts to make sense. Okay? And placing where the windows are, I get criticized all the time. I go, hey, public safety, oh, they got all this glass. Yeah, got all this glass, right? We got all this glass, but the glass is on the north side. And we've got 1/4 of the solar gain on the north side of the building than the south side. So putting the glass in the right place is very important. So on the south side, we probably have 20% wind to wall ratio. This is where all your solar energy comes in. So pay attention to that. Okay, so the other thing is, standard design say, oh, we got to put a ambient, or we have to put light fixtures to get 50-foot candles on the desk so we can work, right? That's been done for 30 years, right? Well, when we looked at that, I go, that's kind of stupid. Why don't we just put the light where it needs to be with the task light and let the ambient be like at 20-foot candles, something that's safe to get around. By taking just this strategy, I was able to reduce lighting power by 50%. Right? I got 140-foot candles on my desk. Nobody complains. Right? Other things you want to consider is regenerative elevators. So it pushes energy back into the building in certain times. And that's becoming standard practice. Computer loads. We have a huge computer center in this particular building. And taking strategies to reduce the loads in that server room was very important. So we used what we call virtual machine software, which means that I have multiple servers on one server by using the software. And so a typical server uses about 220 watts. Using just software alone, I was able to reduce it down to about 17 watts. So 220 to 17, just using software. So very important how you manage your data software. Also, data center, we think that we have to cool those spaces down to about 55 degrees, really cold. Well, nobody needs to do that. We found out that you can keep these data centers to about 85 with no problem whatsoever. And so what we did is we have 100% evaporative cooling through a cooling tower and no chiller at all. None whatsoever. So that's possible. So we can do data centers now without a big chiller system. The other thing is that we want to measure how each employee uses. In fact, we set up a budget that every employee cannot exceed 85 watts at a time. 85 watts. That's your computer, your monitor, all your appliances. And these guys are gadget users, right? They have a bunch of things, right? And so what we wanted to do is enforce that during implementation. So we bought this metric system which monitors every single plug in the entire building for energy use. And so now we can take that and say, workstation 102 uses the most energy in the entire, based on the other employees than anybody else. And so we can now say, why is workstation 102 using so much energy? And probably they plugged in a unit heater or refrigerator or something like that. But so once you figure this out, once you reduce all the loads, then you can come in and do the most expensive mechanical system. So one of the things is we did radiant floors, but we also did radiant heat and cooling. And so now the space is very evenly heated or evenly cooled. And it's very comfortable spaces. Again, very expensive mechanical system, but it's very energy efficient. Yeah.
When you use the radiant systems, how do you control the ventilation to keep the ventilation near a certain temperature or keep the energy down?
That's the next step here. So here's a picture of the PVC. We also use a chill beam system hooked up to the ventilation system. So we're providing just enough ventilation air for each one of the rooms, and if there's any peak, like if somebody walks into a room with 100 people, it actually picks up the load. Right? So we use chill beams, but you could use other systems like water source heat pumps or a variable refrigerant flow system, anything that does heating and cooling inside that zone is what you're trying to get to. So here's a picture of the chill beam system. So the other thing is that you want to train the employees, and this is probably the most unique part of the public safety building, is everybody got it. Everybody got this big idea of being net zero. So we did videos in which every policeman, every fireman had to watch. And they got it. They understand it. So the other thing is that we develop a handbook. A handbook. This is the building, this is the strategies that we use to make this building net zero, and this is how you use the building. So having this handbook that everybody gets, or part of the employee handbook, is very important. Now the other thing, and I'm running out of time, but the thing is that you want to monitor every decisions that go into the design. So what we did is we did an energy model every single week, just to see how our decisions are going. And then we monitor how big the PV array is going to be based on the decisions of that week. So the other thing is that you want to pay attention to tilt of the PV, right? People say, oh, you got to put it at the same latitude angle where you placed it, and that's not true. And if you look here, you can see that about 15% and 40%, the total energy production is about the same. So why not lay them down? Lay them down to 15%. Get more PV on the roof. And granted, you're going to lose a couple months, but those bars are pretty small in terms of energy production. So then we put in the renewable energies, right? Solar hot wire would be one. Here we did a very beautiful integrated PV system that is part of the entrance of the building. It's very beautiful.
So this is right across from the library.
Yeah, this is right across from the library.
See those.
So
Yeah.
the PV is going on the roof as we speak. This is a picture of 2 days ago. And then we have a huge PV, 1 megawatt, being built at the old Redwood dump that was decommissioned in 1960. So that's almost complete. It's probably a month away before that gets 100%. So we've got all this in motion. So let's review, and I'll let you guys go. Can advanced design building be cost effective? Yes, it can be. Public safety building, we're talking less than 10 years of payback. If you do it right, you can get it down to reasonable numbers. 2, can all building types achieve net zero? Yes, that is absolutely true. Public safety is a 24-hour system, plus a data center and everything else. Definitely, you can do it on any building. Can a building located in an urban setting be net zero? That's probably a no. These buildings use too much energy to put all the PV on site. It just doesn't work out, right? And if that's no, which I'm telling you, it's a no, you can't do it. Very specialized condition that you can actually get it to work. Then it's 4. Should we be moving to a net zero city versus a net zero building? And I think that's where we should be going. All right. Well, and I'll be happy to stand around and talk as much as you want.
Wait, I have one question. Do you think you could have designed the data center for the NSA to be net zero?
Absolutely. Just need
I
land.
didn't say.
Just need land. You need a credit card. Absolutely. I mean, your credit cards better be for an off-site bank account, but yeah, anything's possible.
So obviously implicit there, you're just assuming that it's photovoltaic.
Yeah, in this valley, it's basically PV. So wind just doesn't make it.
Okay, so there's two alternatives.
Yeah, basically. You can do other things like, burn waste from forests as a bio system. It just doesn't work. Yes, I know. All right, any other questions?
Why not ground source heat pump?
Doing the systems that I did, it's a lot more energy efficient than a ground source heat pump. There's no comparison. Okay? You can, definitely you can. I would still do the radiant floors. I still would do evaporative cooling. And then the second system could be a ground source heat pump. But there's another reason why you don't do ground source heat pumps in the city urban setting is because you don't have the land. So, yeah.
How are you getting the energy produced by your solar farm out on the dump site into the building? And are you able to bypass dealing with Rocky Mountain Power
Yeah.
altogether?
So, using the greenhouse protocol, right, that's what we're trying to do, is that at the dump, what we're doing is we're generating RECs, renewable energy credits, and selling it to Rocky Mountain Power, right? And we're keeping those RECs. And we're applying those RECs to the public safety building to make it net zero. Okay? That's how we're doing it. And basically, Rocky Mountain Power made a deal with the city to accumulate 3 meters so we can go through just one building to do net metering. So there's a net metering agreement with Rocky Mountain Power to hook up to the grid. We're going through a building to do that. But the protocol allows us to generate the RECs and then use it on another building. So it's all in-house, right? It's all with Salt Lake City, so we can do that.
So because the land where the farm is also on Salt Lake City, within Salt Lake City, not Salt Lake County, within Salt Lake City.
It's city-owned
Same municipality.
city-owned property.
Right. So that's why it can be done if you.
It could be at another land. That's not the issue. The thing is that we're using a greenhouse protocol to generate the RECs so we can apply to the building.
We really need the road. Sorry.
Yeah.
Sorry.
Thank you.